Hello, I'm Rob Weber. I'm the product line manager for the AgileSwitch Digital Programmable Gate Driver line at Microchip. And today we're going to talk about how to tame the Silicon Carbide beast. We all know and love Silicon Carbide and all the benefits that it brings to us as we're doing our power electronics designs. But there are also another side of Silicon Carbide, some of the challenges that get created by trying to drive these devices fast. Noise in the system, plus noise generated by the devices themselves. Short circuit conditions are particularly challenging for silicon carbide, which aren't as robust as IGBT. Overvoltage, another major issue in driving silicon carbide, as well as driving the devices so hot to get overheating. So we've developed a digital approach to controlling the device while also maintaining the highest levels of efficiency and reliability. And in fact, we asked the question, why would you force fit an old analog approach when there's clearly a superior digital solution? Analog solutions were great for silicon switches, but for silicon carbide, analog is irresponsible and unnecessarily dangerous. AgileSwitch drivers tame the SiC beast and unlock the full capability of silicon carbide. So how do we do this? We bring superior digital programmable gate driver technology to the table. And it's a technique we've developed which we call augmented switching. And with augmented switching, we're able to turn the device on and off in a controlled fashion by controlling the voltage level and the time at that level precisely through a direct GUI interface. And by doing this, we're able to reduce false faults, mitigate ringing, lower EMI. We can reduce voltage overshoots and undershoots, and control also current overshoot and undershoot. So what we get is up to 80% lower VDS overshoot, up to 50% lower switching losses, and robust and fast short circuit protection. This is a more precise look, more of a timing diagram look. In your conventional gate drivers, you're turning off in one step, and you're doing that as a hard switch, and then trying to control or modify the gate drivers through gate resistors. With augmented switching, you've got multiple levels that you can precisely control the turn-off of the device. This enables you to use a lower gate resistor, achieve a soft gate transition, and reduce device stress and eliminate the chance of device avalanching. This benefit further continues by cutting development time significantly from both the benchtop testing all the way through to system level production. So today, alternatively, you're swapping out circuit boards, you're changing components, you're burning up boards. With the AgileSwitch system and our intelligent configuration software, you're able to change values on the bench as well as throughout the system development by connecting the gate driver directly to the device. So what are the markets? Today we're focused primarily on higher power, over 20 kilowatts, switching frequencies up to 200 kilohertz. These include some of the industrial markets like wind, energy storage, PV, solar, and we have quite a bit of microgrid activity. However, the major adopting markets today tend to be in transportation, traction, EVs and chargers, heavy-duty vehicles, plus this other interesting segment called induction heating. And this is and happens to be an early adopter market for silicon carbide modules and one that we're very active in today. Now, why do customers choose AgileSwitch drivers? And they've tried others before they've come to join us. So there have been a series of challenges. One is false alarms, short circuit, under voltage conditions, and that can be a result of noise in the system for systems that are not optimized for silicon carbide. Many of our customers go at the design process as they did with IGBTs, but silicon carbide is a whole different animal when it comes to controlling and optimizing the devices. So augmented switching helped here with robust short circuit detection and our protection circuitry. Another design challenge, the short circuit response time was too slow in the application. Old analog technology just didn't allow for the types of speeds necessary to both detect and respond to a short circuit condition, bringing our fast, accurate digital solution to come into play. We have customers with unmanageable voltage overshoot. And again, inefficient internal connection systems, people running wires, cables all over the place. Our precise software configurable tuning helps solve the problems in those situations. Last, insufficient module performance data. Limited driver feedback. That's, again, a major issue with most gate drivers today. We provide over 7 specific fault conditions, including temperature and voltage monitoring. We offer a portfolio of products. Available today, going from right to left here, is our plug-and-play drivers for 1200 volt and 1700 volt modules, as well as 3.3 kV today and planned for the future. We also have in the middle gate driver cores, smaller versions of plug-and-play driver boards for 1200 volt and 1700 volt modules. And while we use our own proprietary gate driver IC today, we will be releasing that as a standalone IC in Q1 2021. This is an example of our plug-and-play gate driver boards. From left to right, you can see our EDEM series. This is a gate driver, plug-and-play gate driver module for your typical Econo-Dual style modules offered by Rohm and others. We have in the middle the 62EM series. This is a very popular product. It's good for up to 1700 volt applications, 10 watts of power per channel, 20 amp gate peak current. And this works and is compatible with the D3 from Microchip, the 62 millimeter modules from Wolfspeed, Infineon, Semitrans, Semicron's C2, and Star Power. And we're also looking at developing 3.3 kV drivers in the XHP and LinPack formats. And all of our drivers feature our patented augmented switching technologies, patented robust short circuit detection and response, temperature and DC link monitoring, 7 unique fault conditions, UVLO, OVLO, overcurrent protection, and our master slave compatible for driving multiple modules in parallel. Our gate driver core provide a unique building block from which you can build your own gate drivers. And the gate drive voltages, both positive and negative, are programmable as well. So it contains all the features in our plug-and-play driver boards. However, again, a building block for you to do your own gate driver. Here's an example of our new offering focused on the new SP6Li modules from Microchip. These are very low inductance modules and can get up to very significant power output. This is a half bridge module, and our gate driver is showing a gate driver core attached to a module adapter board and combined together to provide a single phase leg for this application. Very high power, high voltage levels. The modules are up to 1700 volt rated modules, and the power density again is unsurpassed with these modules. Our adapter board current family is also continuing to grow for the 62 millimeter package, the SP6Li, as I mentioned, the Rohm Econo-Dual style, and the Wolfspeed XM3. And we're continuing to add to our evaluation boards and module adapter boards. Now, these boards are for evaluation purposes. They're designed completely to the standards that you'd require for production purposes, but we only take the adapter boards through to the evaluation stage. We do provide you with all of the files that you could use on your own to produce the adapter boards or modify them for your specific application. The cores are taken all the way through production, and again, you can use them on the bench for development and include them in the final product as you ship that out into the field. To get started, we've put together all the pieces necessary for you to be able to evaluate your product. And to do so, this is showing here everything but the module, is our ASDAC kit. And the ASDAC kit includes 3 gate driver cores, a module adapter board, a Picket controller, including all the cable assemblies, and our ICT software. So whatever module you're using, you can actually use the same kit to test out and look at different module types in your application. Also now, we've just introduced the ASDAC Plus, where we include an SP6Li module, a module adapter board, a gate driver core, and the programming kit as well, including the software. And in fact, we also include the hardware that you need to assemble the devices into a nice, tight little package. And this will take you everywhere from a total system solution approach from evaluation through to production. A little more on the intelligent configuration tool. Here's an example. Here's the startup screen for the tool. And you can see on the left side are control side options. In the center, the gate drive options. And on the right side, the file storage and management system. Along the far left, you can see the core settings. This is the screen we're looking at here. And there are other screens, including graphical editor, some advanced programming and application setting screens, and of course, a help button. What I'm going to show you first is some examples of augmented switching disabled. And we can use the intelligent configuration tool to do this. So we've configured for the gate driver core. We've included a dead time, 600 nanoseconds. We're allowing for control by the controller, but we've turned off all the rest of the functionality at the control side. For the gate driver side, we've programmed the device for +20 and -5 voltage levels. We've disabled our 2-level turn-off. We've continued to enable the short circuit protection, and you can see the values here. So the first example is designed to give you a sense of what does this look like, let's say, compared to a more conventional style gate driver, one where you can't control the device precisely. So you can see 20 volts. We bring it down to -5. And on the right side, you can see the output scope shots. On the blue line, you can see the voltage going up to about 752 volts with some fairly significant ringing, as well as you can see on the current in red, some significant ringing there as well. Turn-off energy of about 11.1 millijoules. And here we're using a 1.1 ohm gate resistor, so a fairly low gate resistor designed to try and optimize for efficiency, but what you see is fairly significant ringing and overshoots. We've now then taken it to the next step. We've turned on our 2-level turn-off. We set the first voltage level at 4.5 volts, 650 nanoseconds. And this is what it looks like on the scope shot. So you can see we've introduced that additional level of turn-off. We have, in the course of doing so, with this first setting, we can show you how we've been able to control the overshoot, control the voltage ringing, control the current ringing as well. But the price to pay is a slight increase in the turnoff energy. So you can see how, with just a slight change in the software, and you can modify these settings, you're able to get improvement in the and your overshoot and your ringing, but at a slight cost or a slight penalty to turn off energy. But let's say you are kind of happy with that, but you still want to see if you can get it a little bit better. See if you can optimize those trade-offs even further. Here we've tried a different level of settings. We go immediately to 0 volts and then a 50 nanoseconds. So this is what it looks like on the screen. Immediate drop to 0 volts. We then hold that for 50 nanoseconds, then we bring it down to the final turn-off level. So what do you see? You see, in this case, a slight increase in the voltage overshoot and ringing, an increase in the current ringing, but we brought the turn-off energy down to 9.9 millijoules. Here again, you can see how through these changes, through these modifications, you're able to dial in to the optimal settings based on the requirements that you have for your application. This is an overview showing you all 3 of these scenarios. So in the first case, 11.1 millijoules of turnoff energy, 752 volts of overshoot, bringing that down and the energy down, or bringing the ringing down but trading off a little bit for energy. So these trade-offs, again, very controllable, very modifiable. We have customers who will express, and these take really no time to test. The beauty as well is that you can do this throughout the development process. So you can do it at the bench. Of course, once you've put your system together, you know that you've introduced new inductances, other variables into the system. You're able to continue by just running a cable into the gate driver, modify these settings to really achieve the optimal values you're looking for. So where are these drivers good today? 20 kilowatts and higher for our cores and for our plug-and-play drivers, where you're using SiC MOSFET modules or you're using IGBTs, but you're considering SiC. And this is a good stepping stone into evaluating SiC. Switch voltage ratings from 600 volts to 1.7 kV today, and we're working on 3.3 kV solutions for the future. Our end applications where we're primarily active are in EVs, chargers, energy storage, trains, trams, trolleys, buses, heavy-duty vehicles, the microgrid, as well as induction heating. Today, under 200 kilohertz switching frequency are typical for us, with wind, solar, motor drives with the above criteria. And with modules today, the SP6Li, the D3, the SP6, the 62 millimeter, XM3, and the EDCA module types as well. So this is, again, I want to thank you for listening in. If you want to reach out to us, you can reach Nitesh Satish. He is accessible. He's based in Bangalore, India, out of APEC and the rest of the world. Cliff Robbins in EMEA and the Americas, and myself, Rob Weber, anywhere. For those of you who'd like to dive in and you want to hang on for a few more moments, take you through some additional test results of conventional versus augmented switching. As shown before, up to 50% lower turnoff losses with augmented switching versus conventional approaches. Here we're using a 1200 volt module, 800 volt DC bus, and there you can't use a conventional driver with a 1 ohm gate resistor. With comparable VDS overshoot, the system with augmented switching has much lower losses. And again, that's another consideration. I was showing you some of the examples earlier where we had ringing levels, but we were operating at lower voltage levels in those examples. Here, in some real life examples, you can see where the benefits truly emerge. So as well, over current tests, we reduce voltage overshoot between typical analog approaches. The other area of importance, of course, and many of you are concerned with, is EMI. Now, fast switching, can augmented switching help with the EMI that's created as a result of fast switching? What we do is we reduce the voltage overshoot and ringing, and thereby reduce the EMI. And you can do this again while optimizing for efficiency in the system. Now, as you know, the main cause of EMI are sharp edges on any signal. And what improves EMI is to smooth the signal. And through our precise tuning for turn on and turn off, we can soften the edges of the gate output. And these edges won't be as sharp because analog circuitry, as well as the external buffer, introduce those sharp edges. So with our approach, you can reduce both radiated and conducted RF emissions. And our precise digital approach can control this, again, through the multi-step process that we bring to the table. And this helps with both radiated and conducted RF immunity. There's quite a bit here of information on the slides. And of course, we're happy to share this information and all of this information with you.